Good morning, my dear NEET warriors. Welcome to the RNA series, your Roar NEET aspirant series, and we are on to our next lecture of oscillations and simple harmonic motion, abbreviated as SHM. One of the most important topics after rotation, considering mechanics, because if you understand SHM, you can understand waves, you can understand oscillations, you can understand light waves, even electromagnetic waves, and there are so many topics on just waves even in some 11th and some 12th standard. So the basis, the foundation is laid over here, and you will see this has a little bit of resemblance to rotation or circular motion also, because at the end of the day we are talking about oscillations, which are repeated motions, periodic motions. So even a circular motion keeps repeating itself after some time, so it has teeny mini bit of resemblance to circular motion, and you will see that in a bit. Alright, so my name is Shreyas, Captain Shreyas, your physics master teacher, training kids for more than 13 years and sending kids just like you for the last 13 years in their dream medical colleges, in their dream colleges year after year. And this year, I hope this is the last year of your NEET preparation, and after this, whatever you do, you will be studying in your desired branch or stream, be it dental, be it Ayurveda, be it homeopathy, be it medical science, be it anything that you love and want to achieve. Alright, so let's begin with the class, and nice to see all of you back after the short Diwali break. Hi Pramukh, Rathiz, Jerusha, Disha, welcome. Yes, your Cap2G is back, and let me show you that today we're going to have some really nice, amazing spring mass system oscillations. We're going to see different things over here. We're going to see how they move, oscillate, everything in today's lecture. Lots of graphs, lots of things, that simulations which will help you visualize like I do in most of my classes, right? So smash the like button. If you have not yet subscribed, subscribe to the Vedantu NEET English channel, the #1 NEET English channel in the entire world, country. Yes. Happy morning, Krishna. Hi, Irfan. Hi, Sneha. Welcome back, Fatima. Hello. Good morning. Let's begin. Now, let's first of all define few terminologies, because those terminologies become important in our due course. Let's start by defining the term called as, oscillations. What is the meaning of the word oscillation? Oscillation is basically to and fro repeated motion. I will give you an example of this. Imagine you have a worried Pandu before the night of the examination, and he is basically reading some book or whatever. He's reading some book like this, maybe. Okay, he's reading some book, and he goes once here and he goes once here. Then he reads something, and then he gets tense. He gets a phone call from his friend, and then he waits for some time, and then again goes over here. Then over here, maybe he eats some snacks, and maybe he drinks some juice which his mom and dad have made. Whatever, he keeps going back and forth. So this is basically an oscillatory motion. Even your Capto, while he is teaching in your YouTube, he is always going to and fro. He is going once here, your teacher is going once here, and then I'm explaining some concept, then again I go over here. Even your Capto is oscillating to and fro, back and forth kind of motion. Repeated motion is called as oscillation. Now, it is not necessary that it is periodic. It is very important. Oscillatory motion may or may not be periodic motion. Now, what is the meaning of periodic motion? I will define on the next slide. Yes, so what is the meaning of a periodic motion? A periodic motion is where it repeats the motion after after regular time intervals, called as the time period, capital T. I'll give you some examples of periodic motion. Imagine you are talking about the moon. The moon goes around the earth. The moon goes around the earth in every 28 days. It repeats whatever it is doing. All the phases of the moon will repeat. Now, this periodic motion is also a circular motion. It is not oscillatory. Another example, you take a thread, you attach some bob over here and you release it. This is basically going to go back and forth, to and fro. It is basically the example of a simple pendulum. This one over here is not only oscillatory, but it is also periodic in nature. This one is not oscillatory, but it is definitely periodic in nature. It is repeating itself. So over here, me going back and forth or this Pandu going back and forth is oscillatory, but it may not be periodic. Maybe I take 1 minute to go here, but I take 2 minutes to come back. Then later on I just go in 5 seconds and then I wait for 1 hour and then I come back over here in 3 minutes. So it is not repeating after a fixed time interval. Hence, it may or may not be periodic. I hope this is clear. Similarly, all periodic motions are not oscillatory. It may or may not be basically oscillatory. It could be anything. It could be circular motion, etc. So I will give you certain examples and we'll come to it in a bit. So what is then the meaning of a simple harmonic motion that we are going to discuss now? Basically, simple harmonic motion. What is the meaning of this? See, I'll tell you what, in this periodic motion, right? In this periodic motion, imagine I'd give you the example graphically like this. Hold on. I'll draw some graphs. And you will think and tell me whether it is periodic or not. Imagine out of all these things, can you guys quickly think and tell me which of the following are periodic in nature? Number 1, number 2, number 3. Come on, let me know. Thank you for lighting up the chat box, Krishna, Madhumati, Newton, Sneha. Thank you so much, guys. Yes, Pratibha, which repeats after regular intervals. All right. So the first one, back and forth, to and fro. Definitely it is oscillatory motion. Oscillatory, yes. Even this is oscillatory motion. This to, fro, back and forth, definitely it is oscillatory motion. But when we talk about periodicity, is this periodic in nature? Yes, it repeats. So is this periodic in nature? Yes. This looks to me like a heartbeat going up and down and repeating the same pattern again and again. So yes, definitely it is periodic in nature. What about this? It is not repeating the same thing. So definitely periodicity wise, it is not periodic. The third one. Yes, correct. Now, out of all of them, there is only one graph There is only one graph which is basically simple harmonic, and that is only this one. This is SHM. This is your simple harmonic motion. This, they are not SHM. SHM, no. SHM, no. This is not simple harmonic. So simple harmonic motion is an oscillation which is periodic, and the graph is a pure sine or a cosine graph, like a speed bump. Peak, valley, valley, peak. It keeps on repeating. A smooth sine or a cosine graph, if it is there, then only it is considered SHM. Any such variations like this, it is not a SHM. It is not a SHM. This is not SHM, guys. Is this clear? So a simple harmonic motion is a periodic oscillation. So it is periodic in nature. It is also oscillatory in nature, with the motion described by a sine or simple cosine function. Simple sine or cosine function. Say for example, this is our x-axis along which the particle is supposed to move. Let's say this is the origin. Right now, let's say the particle is over here. This is our mass. So this becomes our x coordinate. This x coordinate will keep changing because this particle will keep moving. It will keep definitely moving here and there, maybe like this, like this, like this. It keeps moving here and there. So this x which is there, it should be a function. Which function? Sine or cos. So it could be some sine of t, or basically some cos of t. Some sine of t or some cos of t. Something like that will be there. You will see actually the usual manner, the general form of such things is a sine omega t plus phi. We will know what these terms are in a bit. Or you can also write a cos omega t plus phi. So this is the general form of a particle performing SHM. It will be a sine or a cosine function. These are some constants which we will learn in the due course. Don't break your head. Sir, what is this A? What is this A? Hold on, I'll tell you everything. But till this point, is everybody clear? Okay, till this point, is everybody clear? And the graph of that, motion, that is very, very important. If this is your time and this is your position, the graph always should look like a sine or a cos, like this. It will keep on repeating itself. You can see that. It will keep on repeating its pattern. Very good, Tomboy. Jayantika. All right, Pratibha. Very good, Madhumati. Crystal clear. Very good, Sneha Newton. Awesome, Krishna. All right. So somebody, Suchimama, you asked, can a tangent graph? No. Tangent graph, tan, cot, cosec, sec are not periodic. Only speciality of sine and cosine, tan, cot, cosec, sec are not periodic. They are not SHM. They are periodic, but they are not simple harmonic motion. That is very, very important. They are not simple harmonic. Okay, great. So let's understand these things slowly. Look at this spring, look at this mass. Can you see some markings are there on the ground telling you the coordinates on the horizontal axis? And what I will do, I'll just move this around and I will see that, oh my God, look at this. It's coming till here and going till here. This is the maximum displacements that it is having. It is going back and forth, back and forth. I can change the mass also, which is moving. So it will go either faster or it will either go slower. Everything I can do that. I can make the mass big. I can make the spring weak, whatever I want to do. And it will keep on moving accordingly. You can see that right over here. Now, I will make this animation a little fast so that you can see how it is going back and forth, to and fro. Is that right? Okay. If I show the graph of where it is, see how it goes, but I will make it little slower so that you can see it clearly. See, x value. Don't look at this, only look at the orange graph. It's going to and fro. It's looking like a sine cosine graph, right? Look at the orange. These things are velocity, acceleration. We'll come to that later on. Just look at x, the orange line. I'll repeat again. I'll reset. I'll run it again. See how the position graphs are changing. See, it's going up and down. When x is maximum, it is reaching here. See. And when x is 0, it is coming here. When x is negative, it is reaching the bottommost point. Then 0, then maximum. Then again 0, and then negative maximum. So it keeps on repeating its patterns. Is it clear how this works? All right. So now having said that, okay, I can show it to you over here how it moves. See, I take a spring mass system, I make it go up and down. See how it is going. Dub, 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 dub. I can attach more masses also over here, and I can see what happens exactly. Yeah, different mass, and see how it goes. To and fro motions. Yes, definitely. All right. So let's stop this for now. And now let's pay attention to, oh, by the way, guys, if you have not yet smashed the like button, do that. And let me also remind you, the entire PDF will be available to you. Entire PDF will be available to you in the treasure box. The treasure box has all the PDFs, the notes, the YouTube link, everything for biology, physics, chemistry, NCERT line by line, 10-year PYQs, everything are there over here. So this is the treasure box you should be looking forward to. It's absolutely free, of course. You need to enter your login details in Vedantu. It's again free, okay, so that our platform is secure. Correct. All right. So having said this, let's understand what each of these terminologies actually mean. So for that, let me define a few things about simple harmonic motion. So imagine this is our horizontal axis. Okay, this is basically the origin. Let's say the mass which I'm talking about is over here. This is the x coordinate of it, and the x coordinate keeps on changing and reaches some maximum value on either side. Oops. And let's say it reaches from here till here only. So this is the maximum limit on either side. So this mass goes here, crosses this, reaches here, and again comes back. So these are the two extreme positions. They are actually called as extremes only. So they are called as extreme. This is extreme left position, and this one, of course, is the extreme position but towards the right side. You can also say extreme up, extreme down if it is going up and down. If it is going left and right, extreme left, extreme right, you can say that, or extreme up, extreme down. Now, if you have two things exact middle, it is the average. What is the other word for average? Two things extreme, exactly in the middle, it is like averaging both these extremities. So the other word for average is mean position, mean. So hence the middle position is also known as the mean position. What is it called? It is also called as the mean position. X equals to usually the origin. The origin is usually chosen. Usually the origin is chosen as the average or the mean position. Correct. Now having said this, what then is this? From the mean to the extreme right. From the mean to the extreme right, or from the extreme left to the mean. From the extreme left to the mean position. What do you think is this basically going to be called? This is just called as the amplitude. Amplitude, symbol for that is A. Even this is basically A. So this to this is amplitude, this to this is amplitude. Amplitude is the maximum displacement from the average, mean. How much I go this side, how much I go this side. Shreyas Sir while teaching casually wanders off here 1 meter, then he comes back and then goes here 1 meter. So from this side to this side is 2 meters. From the average, I go 1 meter here and then 1 meter over here. So my amplitude becomes 1 meter. If I move 30 centimeters towards the left, come back, 30 centimeters towards the right and come back. So my amplitude will become 0.3 meters or 30 centimeters. That is your amplitude. The next terminology that you need to know is the time period, of course, the time period is basically T. Graphically speaking, I have already shown you how the graph looks like for this. This is your time, this is your position, and the x coordinate might be like this. Oops. And you can see it repeats whatever it is doing, whatever it was here, it is exactly over here after some time. So this then is the time period. Not just that, even from here to here, that is also time period. Even from here to here is also time period, guys. Basically, it will repeat itself after the same time. So you can even go from here to here, it is also time period. Even from here to here is also the same time period. So similar looking points becomes the time period. Then you also have the term called as the frequency. How frequent it is, frequency f, that frequency is 1 by time period. The unit of frequency is basically hertz, which is nothing but 1 by a second, second inverse. 1 hertz means you are completing 1 oscillation in 1 second. 10 hertz means you are completing 10 oscillations in 1 second. That's very fast. Imagine light, etc. have frequency of some mega and gigahertz, meaning millions and billions of oscillations in 1 second. The light waves go up and down in just 1 second. So that is the meaning of megahertz and gigahertz. So the more the hertz, the more number of times it goes up and down. Our vocal cords, they generate sounds in the range of few kilohertz. That means thousands of oscillations per second. So your vocal cords inside your neck are vibrating couple of 100 to 1000 times in 1 second and generating the sound that you are singing or talking around you. Yes, it is hertz, correct. So that was your frequency and this was your time period. You have another term called as the angular frequency. Angular frequency. And this is measured in terms of angle. I'll tell you why. Because usually one oscillation or one time period is usually associated with one revolution in a circle. You can make a mind map like that. Okay, if I go around once, in my imaginary world, I have completed one circular motion. One circular motion is like 2 pi radian or 360 degrees. So usually the world of SHM and the world of uniform circular motion, they are related to each other. We will see the relation in a bit, but you should know this, that one oscillation corresponds to one revolution. One revolution, okay, which means it corresponds. This is not equal to, this is corresponds to. That means it is like it is not equal to. See, if my marks and Pandu's marks are same, okay, I'll say Pandu's marks are equal to Shreyas Sir's marks. So Pandu, you will put 3 lines like that, resembles Shreyas Sir in some ways. So there is some resemblance. So it is like a resemblance symbol. So this is one revolution. One revolution is 360 degrees or basically 2 pi radians. 2 pi radians, or I can also say 360 degrees. Is this okay? 360 degrees or 2 pi radians corresponds to one up and down, one to and fro motion completely. So you define this term called as angular frequency, which is how many radians you cover in 1 second. So that is basically your omega, which is then 2 pi divided by time period. But wait a minute, 1 by t is f, so it is also 2 pi into f. This equation you have already seen in circular motion. Angular speed is 2 pi by the time of circular motion. But over there, omega was angular speed. Don't get confused. Here it is called angular frequency. Formulas look the same, even the dimensions are the same, even the units are the same. Yes, the unit of this angular frequency is still going to be radian per second. That's why I was saying there is some resemblance to circular motion. So for example, I cover one complete round in 1 second. So time period will be 1 second. So omega will be 2 pi by 1, which is 2 pi radians in 1 second. So if I have covered 2 pi radians in 1 second, means I have completed one oscillation in 1 second. Got it? Similarly, if I tell you omega is 4 pi radians per second, what will you imagine? 4 pi radians, sir. So it is 2 times of 2 pi. 2 times of 2 pi. And 2 pi is one oscillation. So 2 into 2 pi means 2 oscillations in 1 second. You are doing 2 rounds in 1 second. So the frequency is 2 hertz. The frequency is 2 hertz, correct? So it means it is 2 hertz. And if you talk about the time period, is f is 2, time is 0.5, makes sense. So it is basically 0.5 seconds. You're just completing one round in 0.5 seconds. So 0.5, 2 rounds in 1 second. 0.5 is 2 rounds in 1 second. 0.5 seconds, 0.5 seconds. Correct? Similarly, my dear warriors, I want you to get the feel of this. If I tell you the oscillation is pi radian per second, what does it mean? Sir, I have not done complete round, sir. I have done half of the round because 2 pi is one oscillation. So pi is half of the round. You have just completed half a round in 1 second. So the frequency will be 0.5 hertz. 0.5 hertz. You can put it over here. If you put omega as pi by f will be 1 by 2, which is 0.5 hertz. So one round, how much time will you take? You are taking half a round, 0.5 seconds. So for complete round, 1 second, you will take 2 seconds. Yes, you will take 2 seconds. So if f is 0.5, time will be 2 seconds. You will complete one round in 2 seconds. That's how it is. So now are you getting a feel of omega, f and t? Omega, f and t. Got it, my dear students? Everyone with me on this? Excellent. Very good. Perfecto. So that is your time period, frequency, angular frequency, how one oscillation is related to one round, which is 2 pi radian, amplitude, extreme right, extreme left, the graph and the position of that particular mass. Excellent. So let's have a look at it here in the graph part. So let's say I go to Desmos. Yes, I go to Desmos and I start typing over here. Okay, so let's say x, or let's say here actually it will be y because we will be doing in the y axis. Y is equal to some constant a, and then where are our functions? Okay, sine, and then omega and t, omega t plus some phi. So that phi symbol, I doubt if it is there here. I don't know. Okay, I'll just type PHI. Oh, we got it. Perfect. So we got it over here. All right. Closing the brackets. Done. Okay. Now get this back. Okay. Amplitude, I can choose what I want. And this is omega t over here and phi over here. Okay, great. So notice how things will change. Notice how things will change over here. I will just ask this to be run. Okay, there you go. Can you see this line is going up and down, up and down? Can you see this line is going up and down? Okay, 1 second. Yeah. Can you see this line is going up and down, correct? Can you see how high it is going and how low it is going? Almost it is going till 4 units because it is amplitude is 3.7. Amplitude is 3.7. Do you see this number outside? That defines how much up and how much down or how much towards the left or right it will go. So, my dear warriors, you can see if I replace this y with x, coming back over here, because usually we use x left and right. So you will see the graph going in the left and right direction. Observe this now. Yes, time will change. See, it is going left and right, left and right. If I change the amplitude, you can see it is going even more towards the left and right. So amplitude is the one which is outside. Amplitude is the one which is outside. Is everybody clear till this point? How it is going back and forth? Okay. Sir, what happens if you change omega, sir? Let's change omega. Omega is 1. What is omega? Number of radians you cover per second. If I increase omega, it will cover more radians per second, which means it will cover more oscillations per second. So it will go more frequently. You will see that. It will go more frequently. See this. Oh my God. Zoop, 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 zoop. Omega is 5.3. I will reduce the omega. So it has become slower, 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 even slow. And actually omega can't be negative. That's the wrong thing over here. So actually you can't have omega. Oops, what is this? Arey, please don't change anything. Yo, why is this step coming? I don't want this step. Okay. Whew. Oh my God. Man, please get my slider back. Where is the slider? Okay, finally. See, omega is less, it will go very less frequently. Omega is more, it will go more frequently. So you can see that over here. Correct? So I hope you understood why x is equal to a sine omega t is now written. The outside term decides the amplitude, the inside term decides how frequent it is. Now you might be wondering, what is this phi, sir? What will it do? What it does is, where does it start from? Observe now. So let's take this time. Time basically will start from 0 and let's say it goes to okay, some 10 seconds, 0.1, okay, enter, okay, and this omega, it can't be, omega is something, see now, it goes back and forth like this. So when time was 0, let's say the amplitude is some 4 meters. When time was 0, where was it exactly? So let me just put over here, just 1 second guys. Let me just set this up. I think now it is fine. See this, phi is 0, okay, perfect. And what I have done, phi is 0. Where was it at time 0? When you started observing it. When you started observing it, where was it? Can you see the red line was at 0? Can you see the red line was at 0, my dear students? Everybody with me? Everybody with me? Can you see the red line is at 0? Yes. And after that, it starts to move. After that, it starts to move left and right, left and right. If I change omega, it will go back and forth more frequently. You can see that. If I change omega, it will go back and forth more frequently. Let's keep omega very less so that you can actually see things in motion. Okay. You can see the amplitude is 4. That's why maximum it goes till -4 and +4. Okay. Now what I will do, I'll change the value of phi. Imagine I put the value of phi as something else. Something else. Now observe. See, where was it at t is equal to 0? It is not at the origin, it is already somewhere else. It is already somewhere else. Yes, you can see that very, very clearly, my dear warriors. In fact, let me keep this as pi 6. Okay. So now observe, I will change the value of phi and see how at time 0 it starts from different positions. Starting off with 0. If phi inside this over here it is 0, it starts from the origin. If phi is something else, it starts from somewhere else. If phi is something else, it starts from somewhere else. If phi is something else, it starts from another point. Again, it starts from different positions. If I choose different values of phi at time 0, that means initially where does it start from? So when phi was 0, it started from the origin. But if phi was, let's say, something else, it starts from some other location only. You can see that. And again, if phi is something else, let's say over here, you can see it starts from some other location here. So where was it at the beginning? So it tells me the situation at the beginning. What is another word for the word situation? Situation. Sir, my situation is very bad. I'm in a very bad phase. Yes, sir. I started very badly, sir. My situation was very bad initially. Sir, I was in a bad phase initially. Are you getting the word now? Yes, it is called as initial phase of the simple harmonic motion. So this phi tells me at t is equal to 0, what was my phase? Was I here? 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 Or was I here? So it tells me where I was initially, initial phase. Correct. That is what it is called. Perfecto. So over here, this particular phi is called as the initial phase of the SHM. Sometimes it is also called as just the phase constant. Just the phase constant. Just the phase constant. This tells me the situation initially. Situation. The situation initially. How was I initially? That is what it tells me. Is this clear? So now we know everything about this equation. Instead of sine, if I use cos, basically instead of starting like this, it will start from maximum. That's the only difference, because sine and cos look very similar. It's just, how it starts, whether it starts from origin or whether it starts from maximum. That's the only difference. Otherwise, you can use them interchangeably. There is no harm. Some books will use sine, some books will use cos. Don't say sir taught sine, but in the exam paper cos came. They are exactly the same things, guys. Don't worry. Okay, cool. So that is how your SHM parameters are. So now we know basically A stands for amplitude, omega stands for frequency, angular wise, and phi stands for the initial situation. Let's do some examples on this so that we can move forward after that. Okay. Say for example, here is the question. X is equal to 0.5 sine 4 pi, let's say 8 pi t plus pi by, let's say 6 pi by 6. Okay, meters. The questions are, find Number 1, the amplitude. Number 2, the angular frequency. Number 3, the time period. Number 4, the frequency. Number 5, the initial position. Okay, these are the things that you need to figure out from this equation. Let's try and solve this, my dear students. Look at this equation and compare it with x is equal to a sine omega t plus phi. Automatically you will start getting everything. From this, it is very, very obvious that the amplitude is like 0.5. So the amplitude is 0.5 meters. Done, dusted. Amplitude is 0.5 meters. Perfect. What is omega? Direct comparison will lead you to 8 pi radian per second. But omega is 2 pi by time period. So that is basically 8 pi. Therefore, the time period will be 2 pi divided by 8 pi. So that means it is nothing but 1 by 4, which is nothing but 0.25 seconds. So the time period is 0.25 seconds. Once I get time period, we can also find frequency. Frequency is 1 by time period. So 1 by 0.25, which is basically 4 hertz. So it is basically 4 hertz is the frequency, 4 oscillations in 1 second. That is also done. What about initial position? See, the moment initial word is used, that means time is 0. So when time is 0, the value of x at 0, time will be 0.5, put 0.5, sine omega into t, time itself is 0, plus pi by 6. Pi by 6 means 30 degree. Sine 30 is basically nothing but half. Sine 30 is nothing but half. So half into half is 1/4. So it will be 0.25 meters. So that is original initial position. Initial position. Is that clear, everyone? Understood how to solve and get the answers to this question? But there could be more questions also to this. Let's say we ask some more things. And the next few things that you need to find, also find the next thing, sixth thing which you need to find is where is it at t is equal to, let's say 0.25 or let's say 0.125 seconds. Then the next thing that you need to figure out, when is it at x is equal to when is it at x is equal to 0.5 meters? That is the next question over here. Okay, so try to solve this. These are additional questions in the same thing. When is it at x equals to 0.5? Where is it at t is equal to 0.125 seconds? Let's try to solve it one by one. The first part says time is equal to 0.125. So why not just substitute it here and we'll get the answer. So x will be equal to 0.5 sine of 8 pi and then you have 0.125 plus pi by 6. Now what do you do over here? What is 8 into 0.125? What is 8 into 0.125? It is nothing but 1. Yes, 125 into 8 is basically 125 into 8 is nothing but basically 1000. So 0.125 into 8 is just going to be the number 1, isn't it? So it is just going to be the number pi plus pi by 6. Now use your trigonometry rules. Sine of 180 plus something. First of all, this number which you see over here is in the second quadrant. In the second quadrant, all silver teacups. Second quadrant sign is basically positive. So the answer is 100% 100% going to be a positive number. Okay, that is decided. When you have sine of 90 plus something, then sine becomes cos. If it is 180 plus minus something, then sine remains as sine. So it will remain as sine of pi by 6 only. And sine of pi by 6, my dear students, that is sine of 30, which is nothing but what? Yes, it is 1 by 2. So it is basically at 0.25 meters. So it is basically at 0.25 meters. Is this absolutely clear? Yes, perfect. Yes, 1 by 4 also will do, Krishna. Correct. That was the first part. Second part, when is it at x equals to 0.5? So let's substitute the value of x as 0.5. Okay, so I'll get 0.5 is equal to 0.5 sine 8 pi t plus pi by 6. 0.5 cancels. So sine of 8 pi t plus pi by 6 will be 1. Whose sine is 1? When is the sine value going to be 1? When it is 90, right? So basically the inside term 8 pi t plus pi by 6 should be basically 90. 90 means pi by 2, correct? Therefore, 8 pi t will be 90 minus 30, which is 60. So it is basically pi by 3. It is basically pi by 3. 90 minus 30. If you take pi by 6 on the other side, yes, it will become 60 degrees, which is pi by 3. Pi cancels, so 8t will be 1 by 3. Therefore, time will be 8 3s are 24. So 1 by 24th of a second. So at 1 by 24th of a second, it will be at 0.5 meters. Do not put 90 degrees here, because if you put 90, then it will not match dimensionally, units wise, because left hand side is in radian, right hand side will be degrees. So ensure everything is substituted in radian, especially for SHM. Don't do it in degrees. Okay, very good, Madhumati Sneha. Understood? Oh, clear? Oh, perfect. Awesomeness. Let's do the next amazing question coming up on your screen. Let's do another amazing question on your screen. So for a SHM with amplitude A and angular frequency omega, what is number 1 average velocity, number 2 average speed for one complete oscillation? That is the question. For one complete oscillation, what is the average speed and what is the average velocity? That is the question. Come on, think about it. In one complete oscillation, I will go towards the extreme right, I will come back over here, I'll go towards the extreme left, and I will come back over here. This was my mean position. This is amplitude. This is also amplitude. If you see, I have come back to the same position after one complete oscillation. So after one complete oscillation, the displacement is 0 because you come back to the same location. So displacement is 0. Therefore, the average velocity of a SHM is always going to be 0. Yes, the average velocity is going to be 0 for a SHM. But what about average speed? I don't think that will be 0, because average speed is the distance, is basically the distance in one oscillation upon the time which you take in one complete oscillation. How much distance you travel? A, and then A. So A how many times, guys? 4 times. So 4 times of A, correct. And time is basically T. But wait a minute, I know time formula. It is 2 pi divided by omega. So therefore, omega will go on the top. 4 and 2 will cancel. So 2A omega divided by pi is your average speed, which is definitely not a 0. Average velocity is a 0. Average speed isn't a 0. Is this clear? Yes. Big fat 0 for average velocity. Perfect. Awesomeness. So these are some of the questions which you can get on this. We'll do one more question, but that will involve cos, so that you are habituated. No matter what, I can do it. Let's say x is equal to 3 cos pi t plus pi by 3 over here. Okay, let me make this 6. Okay. Question is find number 1 the initial position, number 2 just the frequency, initial position, number 2 the frequency, number 3 the time when x is equal to 0 meters. The time when x is equal to 0 meters. So these are the 3 questions that we need to solve. Let's solve it one by one. Initial position is asked. Let's try to solve that first. Initial position means initial position means you have to substitute time as 0 over here. So x naught when time is 0, 6 sine, time is 0, so 0 into pi is 0, plus pi by, sorry, this is not sine, this is cos, my bad, 6 cos 0 plus pi by 3. So this will be 6 cos of just pi by 3. What is pi by 3? Pi by 3 is basically 60 degrees. Pi by 3 is nothing but 60 degrees. Cos 60 is half, so it will be 6 multiplied by half, which is nothing but 3 meters. So the initial position we have done, it is nothing but answer is 3 meters. Everyone fine? So it started from the one of the not origin point, x is equal to 3 meters. Yes, it did not start from the origin. Next problem. What is the frequency? So for that, compare, you will see omega is basically pi, but omega is also 2 pi f. So 2 pi f is pi by. So 2f is basically 1. Therefore, f is half, which is nothing but 0.5 hertz. So this second part is also done. Frequency is 0.5 hertz. Okay. The time when x is equal to 0. So x value has to be substituted as 0. So 0 is equal to 6 cos pi t plus pi by 3. That means the value of the cos pi t plus pi by 3, anything into 0 is 0. So 6 can't be 0. So cos has to be 0. So cos of this should be 0. Whose cos is 0? Cos 0 is 1. Cos 90 is 0. So the inside term must be 90 degree, but we never do it in degrees. We always do it in radians. Correct. So you will put pi by 2 radian. So therefore pi t, take this on the other side. 90 minus 60 is 30. So it will be pi by 6. So pi cancels. I will get it 1 by 6 seconds. So the time is 1 by 6 seconds when the value of x is 0. That means it comes back to the origin. Clear, everyone? Are you now confident about solving these questions? Are you now confident about solving these questions? Yes or no? Quickly think and tell me. We have done all the kind of numericals that you can get related to time, phase, frequency, angular frequency, sine, cos, everything. Cool? So I think now you got a fair idea. Okay. Great, sir. Sir, can you now tell me, can we find velocity, acceleration, kinetic energy, etc. also? The answer to that is yes. The answer to that is yes. We'll try to find all these things now one by one. So observe this. Observe this. X was a sine omega t. Okay. Let's say plus 5. Example. Then, in order to find the velocity of the particle, the particle will have some velocity, okay, and then in the later on stage it will also be required to find the acceleration. How do I find that? So now we all know velocity is just the derivative of the position dx by dt. So in the term x, a is a constant, so a comes outside, and I will be required to only find the derivative of sine of omega t plus phi. But derivative of sine is nothing but cosine, so it will be a. Instead of sine, you will have cos omega t plus phi. Do not forget, because I am differentiating with respect to time, whatever multiplies with time comes outside. This is the ax plus b rule. So omega will come outside, and hence this is the velocity. So you are supposed to again remember this. All these are important formulas. Velocity is a omega cos omega t plus phi. All these formulas are very, very important. So I'll in fact start marking all these formulas. This one, of course, this is obviously very important. All these things are your formulas. Correct. All right. Till this point, I hope it is absolutely clear. This is for your velocity. We'll similarly do it for acceleration also. Observe this now. Now, since velocity is nothing but a omega cos omega t plus phi, okay, this is what we got, a omega. So basically when omega came and sine became cos, if this was cos, this would have become negative sine. Getting my point? If x was a cosine function, derivative of cos would be negative sine. So negative sine would come here, and still that a omega would have stayed outside. That's all. That's the only difference. So a cos omega t plus phi, but we all know that acceleration is nothing but the derivative of the velocity. So that a will come outside, it's a constant, and you will just be required to take the derivative of cos omega t plus phi. Okay, let's see what the acceleration will come out to be. A is as it is, a omega will also come outside. Derivative of cos is a negative term, negative sine omega t plus phi. Do not forget even that omega will come outside. So again one omega will come. So it will become minus a omega square sine of omega t plus phi. So this is the answer for your acceleration. Every time you differentiate, whatever term multiplies with this time will come outside. Okay, that is your ax plus b rule of your derivatives. Those of you who have forgotten that rule, let me remind you of that rule very, very quickly. If derivative of some function with respect to x is something, then derivative of ax plus b with respect to x, it's of this form. You will see it is g of ax plus b. It's just that this number will come outside. You will multiply it with a. That's the formula. So this is your ax plus b rule. Correct. So we found acceleration. We also found velocity. Now let's do one more thing over here. Let's proceed with this velocity and let's do something very interesting to it. Observe it very carefully. My dear students. Now, okay, what I'm going to do, I'm going to write cos omega t plus phi. Cos omega t plus phi will be v divided by a omega. Now, how about writing cos square omega t plus phi plus sine square omega t plus phi? What do you think the answer to this will be? Cos square plus sine square. This is a standard trigonometric identity. Cos and sine squared being added, the answer is always 1. So cos square means I have to do this guy's square. So velocity square by a square omega square. What is sine square, you might ask? What is basically sine square? Well, sine square is there right over here. If you notice, yes, sine of omega t plus phi is nothing but, take a below, so it is just x by a. So strictly speaking, it is x square by a square. So this whole thing is nothing but 1. This whole thing is nothing but 1. We will play around with this, multiply the entire equation with a square omega square. Multiply the entire equation with a square omega square. So it will become v square plus x square omega square will be a square omega square. Therefore, v square will be omega square a square minus omega square x square. So omega square is common, and what I'm left with is a square minus x square. Okay, take root on both sides. So velocity will be omega root of a square minus x square. This is another important formula where x is given, velocity can be found. Here time is given, velocity can be found. If position is given, velocity can be found from here. Got it? So it's a very interesting thing over here. How you can relate velocity with time or velocity with position. A very similar analysis can also be done over here. What I can do, I can write this acceleration as minus omega square first, then this a sine omega t plus phi over here. Now you might be wondering why I did it like this. What is this a sine omega t plus phi? A sine omega t plus phi is basically x, correct? So therefore, I can replace this with x and I will get this as minus omega square x. So acceleration is minus omega square x. Acceleration is minus omega square x. Very, very important thing. Cool till this point? So acceleration in terms of time, acceleration in terms of position, velocity in terms of time, velocity in terms of position, everything done. Are there graphs also related to it? Yes, we can see the graphs. But before going ahead to the graphs, let me show you one important thing. Cos can maximum go to 1, least go to -1. Magnitude wise, the value of cos can be maximum 1 and least magnitude wise, modulus wise 0. So this value can't go beyond 1, can't go below 0 magnitude wise. So the velocity magnitude, which is the speed, can maximum go a omega into 1 times, can least go a omega into 0 times. Hence, you will see that the maximum speed, which means the modulus of the velocity is going to be a times of omega, and the minimum speed of the particle, modulus of the velocity, is going to be a big fat 0, because the cos minimum value of cos is 0 and the maximum value of the cos, maximum magnitude of the cos is 1 magnitude wise. All this is magnitude wise because we are calculating the speed. Is this absolutely clear, guys? Why the maximum speed is a omega, minimum speed is 0. Now can you think and tell me where would this maximum speed be? Just imagine your captain Shreyas Sir going back and forth like this. Where do you think my speed is maximum? If you are not able to visualize, no issues. We'll come back to this oscillation over here. Where do you think is the speed maximum? I think here you stop. Here also you stop. I think here the speed is maximum. When you're crossing through the average or the mean position. You can see that even over here. If I run this in probably little bit faster mode, you can see. Here I stop. Maximum speed 0, maximum speed decelerate stop, maximum speed accelerate, decelerate stop. Yes, correct. So hence my maximum speed is going to be where? at the mean position. At the mean position. If you ask me where the minimum speed is, it is going to be at any of the extreme positions. Extreme positions, correct. So extreme right and extreme left, the speed is going to be 0. And at the mean position, whether you are going like this or you are going like this, the speed is going to be maximum, whose value is going to be a omega, correct. The maximum speed is going to be at the mean position. Is this clear, everyone? Yeah. Thank you for reminding me to have water. Yes, let's also see for acceleration now. Before that, if you want to see this once more, just have a look at it. Similarly, if you go for acceleration, see this sine term over here. Again, the maximum value of the sine, magnitude wise, maximum value will be 1. And of course, the least value, minimum value, will be obviously 0. So if you ask me, where is the acceleration's magnitude going to be maximum? The answer will be, first of all, the maximum value will be a omega square, and the least magnitude of the acceleration will be 0, because least value of sine is 0. So 0 into anything is 0. Maximum value, which is 1. 1 into a omega square will be a omega square. So where will it be 0? Where will it be maximum? Don't go from this, go from this equation. It will be very obvious. When x is 0, a is 0. When x is maximum, a is maximum. So when is x 0? A is 0. That means x is 0, x is 0. That means over here. So this is exactly opposite. So this is at the mean position, it is having the least value. I think I wrote maximum by mistake. So this was a minimum, my bad. So at the mean position, it has the least value. So it is 0 over here. Acceleration is minimum. In fact, it is 0 at the mean position. And at the extreme position, because x will be maximum, a will be also maximum. X is equal to a omega square. So hence, this will be at the extreme positions. Extreme positions. So here you will see the acceleration is maximum. Acceleration is maximum. Even here, the acceleration is going to be maximum. Notice how the direction of the acceleration is also shown. Why did I not show acceleration that way? Is because I know acceleration is negative of x. So when x is positive, acceleration is negative. When x is negative, acceleration is positive. That's why for the negative coordinates, acceleration is towards the positive direction. For the positive coordinates, acceleration is towards the negative direction. That's because of this negative sign here. Is this clear? Understood? All these things are very, very important. Okay. Talking now about the graphs of all these things, very important again. The graphs. Time. This is position, this is velocity, this is acceleration. Okay, so say for example, the position time graph is like this. I'll do one thing. Okay, fair enough. Let's say position time graph is something like this. the maximum value and the minimum value will be plus A and minus A, which is the maximum position and the least position, minus A and plus A, right? So this is where it is plus A. Here the position is going to be negative A. This is for position, and I have assumed X is basically, let's say, A sine of omega t. What will the velocity graph be? Think about it. What will the velocity graph be? Velocity graph, the derivative of this, it will be A omega cos omega t. If it is sine, it will be cos. If it is cos, it is sine. So omega is that extra multiplying factor outside. So it will be like a cos function. So cos function will look something, oops. So you can see one cycle is completed here, and it starts from A omega, goes to minus A omega, and again comes back to A omega in one time period. By the way, this is one time period, this is 2 times of time period. This is time period by 2. Yes, this is half of the time period. Correct. So this one thing is one time period. Okay, I hope you are able to see that. What about acceleration, guys? Acceleration is minus A omega square. It will come back to sine now, right? It will come back to sine. You can see that acceleration comes back to sine. Yes. So if it is sine graph, it should look like this, but because of the negative sign, instead of going up and down, it will start with down and then go up. So it will start with down. Yes, it will start with down first and then go up. Correct. It will start with down and then go up. And this maximum value is A omega square. The least value is minus A omega square. Very, very important. Is this absolutely clear, my dear students? Perfect. Now, having said this, there are 2 more graphs which you should definitely know. One of them is this one over here. Again for acceleration only, but it is acceleration versus x. This is acceleration and this is x. We know how acceleration is related to x. It is negative omega square x. It is directly proportional to x, but with a negative sign. That means it has to be a straight line, but with a negative slope. Hence the graph of this is something like this. This is how it goes. Yep. This is how exactly it goes. And this is maximum value of A omega square. And this will be at negative A. This at plus A has a value of minus A omega square. So that is acceleration versus position graph. Again, you should be aware of it. Next and the last thing is for velocity. Now you just have to know this. You don't have to get into the details or why it is like that. Just remember velocity and x. Velocity and x. Where is it? Velocity and x? Right over here. This equation. Velocity as a function of x. No, it is not a parabola. It is not a quadratic exactly. It is actually going to be an ellipse. It is actually going to be an ellipse, something like this. So this is the graph. This is the graph of this. Yep. And you will see the maximum value of x is plus a, the least value of x is minus a, the maximum value of velocity is a omega, the least value of velocity magnitude wise is 0, but if you consider the sign, it is minus a omega in the opposite direction. So this is an ellipse, very, very important. It's an ellipse. This was basically a straight line. This was basically a straight line. This was a bumpy road, up and down motion. Okay. So all the graphs I have shown you for position, velocity, acceleration, as well as their equations as well over here. So I think it's a good time that we start with some questions onto that. But before going to the question, one last thing I will tell you and then we will start off with it. Okay, observe. Since this particle is going back and forth and it is also having some acceleration, if I'm interested in how much force is acting on the particle, how much force is acting on the particle to cause that acceleration. So the net force on the particle executing SHM, F will be mass times the acceleration. Mass times the acceleration. But acceleration is minus omega square x. Okay. So F is minus m omega square x. F is nothing but minus m omega square x. So now I have an interesting thing to write down over here. Observe this, m omega square into basically your x. Usually the force which is acting on a mass is like a spring which is trying to pull it back and forth, like the one over here. Look at this. When this is going back and forth, what is that force going to be actually? It is going to be the spring force, and we know spring forces are like kx, negative kx. So actually this term which is here, this term which is over here, m omega square, shouldn't this be k, which is nothing but your spring constant, my dear warriors? Shouldn't this be like your spring constant, my dear students? Yes or no? Correct? So we now got k, therefore is nothing but m omega square. Therefore omega is nothing but root of k by m. A very important formula which I feel you should remember for solving many of the questions. Omega is root k over m. But also we know omega is 2 pi by time period. So therefore I also get the time period as 2 pi root of m by k. So this is the time period of oscillation of a simple harmonic motion like a spring, where you have, instead of this, imagine there is a spring over here which is attached to this particular mass. Spring which is over here which is attached to this particular mass. Then it will behave like a spring force, like kx. Comparing m omega square with k, you can see f is minus kx, f is minus m omega square x. So m omega square is like k. Omega I will get k by m under the root, but omega was also 2 pi by t. So taking time on the top, time is 2 pi root m by k. That is the answer. Very, very important. So see this, if mass is heavy, time will be more. If mass is less, time will be less. K is more, very strong spring, time will be less. K is less, time will be more. Let's see whether it is actually true or not. Let's try this. Let's take the mass of the block to be very, very small. Mass is very, very small. Let's see what happens. Oh my god, it is going back and forth very quickly. Time of oscillation is very low. If I increase the mass, see now what happens. If I increase the mass very slowly, huge mass. So that means time has increased. It is taking more time. It is taking more time to go back and forth. Okay, if I reduce the mass, it goes back and forth very quickly, just as we expect here. If mass is less, time is also going to be less. Now let's see what happens when I change k. Look at this. It is going back and forth now. Okay, like this. It is taking some time to go back and forth. Okay, let's reset this and let's increase the spring constant. See what will happen. It will if k increases, time will reduce. It will come back very quickly because the spring is stiff. It will pull it back with a large force. It is coming back really quick. If I reduce this, it will come back very slowly. See, aram se it is coming. Very coolly it is coming. Very coolly it is coming. If I again increase the value of k and run it, it will come back little bit quicker. It will come back a little bit quicker. Also notice how if position is like this, velocity is like this, how acceleration is like this. Can you see that, my dear warriors? Yeah, I hope you are able to see this. How the graphs, just like we plotted some time back for position, velocity, acceleration, exactly like this. All right, I hope everybody is able to see this. Very nice, awesome, great. So these were some of the equations. Can we also write kinetic energy and potential energy of those masses? I think so. If this is the velocity of the particle and imagine there was a spring-like thing over here, can we also write the kinetic energy and potential energy? Definitely, why not? Kinetic energy is nothing but half m v square. So I can write this as half m. Remember velocity, I just told you some time back. Where is it? Omega root a square minus x square. So why not use that over here? So it will be omega root a square minus x square. The whole thing is square. Therefore, k will be equal to half m omega square a square minus x square. But wait a minute, m omega square. I think I know what m omega square is. M times omega square is k. M times omega square is k. But don't get confused with this k, that is kinetic energy. So maybe I will use a different symbol over here just to avoid the confusion. So it is kinetic energy. This is kinetic energy. We are talking about kinetic energy over here. Okay, will be half, instead of m omega square, I will use spring constant. And this will be a square minus x square. Perfect. So that is your kinetic energy. What about potential energy? Potential energy is basically potential energy of a spring formula. And what is the potential energy of a spring formula, my dear warriors? It is just half k x square. It is just half k x square. Correct. Now what I do is basically I will add both of them. And see what do I get as the answer. Basically we are talking about the total mechanical energy, which is nothing but your kinetic energy, and you add to it the potential energy. So what is the kinetic energy? It is basically half k a square minus x square. Okay. What is the potential energy? It is half k x square. So think about it. Half k negative x square, half k positive x square. They will cancel and I will be only left with half k into amplitude square. So that is the total mechanical energy. That is the total mechanical energy of that particular thing. And I think we should block this. And observe, it is half k into a square. A is the amplitude. So neither a will change nor k will change. Half is a constant. So this is obviously going to be a constant. It kind of makes sense that the total energy should be conserved. Constant means it is conserved. Spring gets converted into kinetic, kinetic gets converted into potential, and that interconversion keeps on happening. And we can see that right over here. If I see the energy graph, let's run this and see how it looks like. Okay, it is really fast. Let me make it slower. Okay, let's see. See, now when it is here, most of the energy is kinetic. When it reaches the extreme, the red one is potential energy. When it is at the mean, it is all kinetic. When it goes here, it becomes again potential. Again, everything is kinetic. Now everything slowly gets converted into potential. But the total energy of kinetic plus potential remains constant. We can also see the energy graph over here, which is very interesting. When it is at the mean position, the green graph, which is kinetic energy, is maximum. See, maximum kinetic energy. When it reaches the extreme, it is 0. Again, mean position maximum. Again, minimum kinetic energy because it stops. Potential energy wise, here the spring is at natural length. So potential energy stored is 0. Again, when it gets compressed, maximum energy gets stored. Again, spring energy becomes 0, and again it gets extended, becomes maximum. Again it comes back to 0 spring potential energy. So one increases, other decreases, other decreases, this increases. The total sum will remain a constant. It's a beautiful visualization, isn't it? Yeah. So I think we should also put that visualization graph over here as well, so that it is there in your notes. So what is there on the horizontal and vertical lines? Vertical is basically your energy. Vertical is basically your energy. Horizontal is basically your position, basically x. The constant line is over here. This is your energy line. This is your energy line, something like this. And it will obviously be till here and till here. This is x equals to minus a. This is x equals to plus a. The value at which this cuts the energy line is half k a square, which is the energy of SHM. And spring potential energy will be like this. This is your spring potential energy. It is a parabola again. Parabola. Yes, because it is square term here, it is a parabola. And the kinetic energy graph, it's inverted parabola. So this one over here, this is kinetic energy. This is also a parabola. Inverted. Inverted. Okay. So that's how the graphs will look like. The total sum will be a constant. Clear till this point, everyone? Shall we now start doing some questions on this? Yep, ready for some questions, and then we'll have a break before we again return. Okay, so go through all the formulas once more, because a lot of equations we have done. Starting off with velocity is a omega cos omega t plus phi, because x was sine. Also written down in terms of omega root a square minus x square. Maximum speed is at the mean. Extreme positions, it comes to rest for a brief moment. Acceleration wise, it is negative a omega square sine term. Maximum is at the extremes and minimum is at origin, or basically the mean position. You can also write acceleration as negative omega square x. Position, velocity, acceleration, they are all sines, cosines only. Only acceleration versus x is a straight line, and velocity versus x is a elliptical graph. Next thing, omega is root k by m. Time of a simple harmonic motion is m by k root 2 pi. K is the spring constant of the mass which is attached to the spring. Okay. Total energy is always a constant, kinetic plus potential. Potential is half k x square. Kinetic is half k a square minus x square. The graphs look like parabolas. One is U-shaped, another is inverted U-shaped parabola. Their sum is always going to be conserved. These are the terms that we have learnt over here. So let's start doing some questions. Okay, let's start doing some questions. Here is the question coming up on your screen. Question is, find number 1 time period, number 2 frequency, number 3 omega. It is also given that the maximum displacement from the mean position is 0.5 meters. 0.5 meters, that is also given to us. So, okay. Next thing, the fourth thing, maximum speed. Fifth thing, maximum acceleration. All these things you have to find. Okay, come on, let's try to solve this question. It's a spring mass system. It's a spring mass system. So, you know, spring constant is given, mass is given, maximum displacement from the mean is also given. So, you know, most of the values are already given to me. Maximum displacement is given means This whole thing just means that the amplitude is 0.5 meters. Okay, so let's start by finding the time period. Time period is 2 pi root mass by the spring constant. 2 pi is as it is, mass is 4 kg, spring constant is basically 100. Root of 4 is 2, root of 100 is 10, 2 goes with 10 5 times, so hence the time period is 2 pi divided by 5 seconds. So that is the time period. Let's find out the frequency, which is 1 by time period. So it will be 5 divided by 2 pi hertz. That is your frequency. Okay, what about omega? Omega is nothing but 2 pi multiplied by f. So 2 pi multiplied by frequency, which is 5 by 2 pi. 2 pi cancels, so it will become 5 radians per second. So 5 radians per second is your omega. We got that. Next, so since we have found out time period, frequency and omega, next is maximum speed and maximum acceleration. Maximum speed is nothing but how much, guys? It is nothing but a omega. So amplitude is 0.5. Omega, we just got it from here. So 5 5s are 25. So 2.5 meters per second is the maximum speed with which it can travel. What about, so this is done. What about maximum acceleration? It is nothing but a omega square. So 0.5 is the amplitude. 0.5 is the amplitude. Omega square means 5 square. So 25 into 5, 125, 1 decimal. So 12.5 meters per second square. That is the answer. So solved. Got it? Very straightforward. Shall we move ahead? Very good, Krishna, Sneha, awesome. Keep it up, guys. And those of you who are late joining in, make sure not only you mark your attendance, also subscribe to the channel so that you do not miss any notification about the academic sessions which will follow. Also, make sure that you watch the lecture in the recorded form later on in case you missed watching the live. It's okay, even if you watch it recorded, it's not like you are going to lose anything. Sir told something during live which I did not watch, nothing like that. Okay, next question on your screen. Here it is. Actually, a continuation of this only. Okay, so we found out 5 things. Next thing, the 6th thing is the total energy of SHM. Total energy of SHM. 7th, kinetic and potential energy at x equals to 0.2 meters. That is the question. Come on, let's see if you guys can figure this out. Kinetic and potential at x equals to 0.2 meters and the total energy of SHM. We know the total energy of SHM formula actually. The total mechanical energy of SHM is given by half spring constant into amplitude square. Spring constant, we know it is 100. Okay. Amplitude is nothing but 0.5. So 0.5 square. So this will be half multiplied by 100 multiplied by 0.5 is half. Half square is 1 by 4. Now 100 by 4 is 25. 25 by 2 is 12.5. So 12.5 joules. So 12.5 joules is the total mechanical energy. So this part is done. Okay, cool. Let's move ahead to the next part of the question. Total energy is 12.5 joules. How much is kinetic and potential at 0.2 meters? I think finding potential energy is usually the easier method. Potential energy is half k x square. Spring constant is basically 100. The position is 0.2, so 0.2 square. So 1 by 2 into 100. 0.2 is basically 1 by 5. So 1 by 5 square. So it is 1 by 25. Correct? 0.2 is 1/5. So 1/5 square is 1 by 25. 100 by 25 or 2 into 25 is 50. 100 by 50 is basically 2. So 2 joules is the potential energy. 2 joules is the potential energy. What about What about the kinetic energy? Well, we know kinetic energy plus potential energy is the total mechanical energy because energy is conserved. So kinetic energy will be mechanical energy, which is 12.5. Subtract from that 2 joules, you will get 10.5 joules of energy. So that is the kinetic energy of the particle at that location. Correct. So that's how you solve this. So this also done and dusted. Perfect. Let's move to the next question coming up on your screen. Here is the next question. If maximum speed is, let's say, 6 pi meters per second, maximum acceleration is given to be, let's say, 12 pi meters per second square, 12 pi square meters per second square. Okay. 24 pi square meters per second square. And the question asked is, find omega. Can you also find the amplitude of that particular particle? Can you find omega and also find the amplitude of that SHM? Maximum speed is given, maximum acceleration is also given. Find omega and also find amplitude. Let's see if we can do this. Okay. First of all, what's the formula for maximum speed? For maximum speed, my dear warriors, the formula is omega into A is maximum speed, and that is clearly given to be 6 pi. Okay, that's one thing. Next thing, acceleration. What's the formula? It is omega square A, that's the maximum acceleration, which is given to be 24 pi square. I have an idea over here. Instead of writing omega square A, why not write it as omega into omega A into basically omega A. This is equal to 24 pi square. What is this omega A? Omega A is basically maximum speed, which is nothing but 6 pi. Oh, perfect. So now I think we can get the answer of omega from this. Therefore, omega 6 goes with 24, 4 times pi and pi cancel, so 4 pi. So omega is 4 pi radians per second. We got the answer. Omega is 4 pi radians per second. A seemingly tricky question can be solved with some manipulation. Once you get omega, we can solve this also. See this? Omega is basically 4 pi. So 4 pi multiplied by amplitude is basically 6 pi. Therefore, pi cancels. So 4a is equal to 6. So amplitude is 6 by 4, which is also 3 by 2, or basically amplitude is 1.5 meters. So we found the amplitude also, we found omega also. Some people are cheating already. Come on guys, prove that you are not that NEET 2024 person. You are not a cheater by smashing that like button, not just putting it on the polls. Yeah, smash that like button, make it 100 likes plus now already. Correct. Cool. Okay, so that is how you solve this. Let's move to the next question coming up on your screen. Here it is. If amplitude is 5 meters, time period of oscillation is 2 seconds, find number 1, maximum speed and acceleration. Number 2, the speed and acceleration at x equals to 3 meters. Two kinds of questions. Find the maximum speed and acceleration. Also find out what is the speed and acceleration when x is 3. Obviously 3 is somewhere in between, so it will not be, exactly maximum nor minimum. Let's try to do this. Let's do the first problem. Maximum speed and acceleration has a direct formula. Maximum speed is a omega and maximum acceleration is a omega square. But the problem is I do not know omega. Amplitude I know is 5. Amplitude I know is 5. What is omega? So from the time period, I think we can find omega. Omega was 2 pi divided by time period. So 2 pi divided by 2, 2 cancels. So it will be pi radian per second. So here omega I will put it as pi. And over here I should put pi square. So the correct answer over here for maximum speed will be 5 pi meters per second. And for acceleration it will be 5 pi square meters per second square. So this is done. This is done. The first part is done. How about the second part now? What is the speed and acceleration at x equals to 3? I think acceleration is very easy to find at x equals to 3. Use the formula omega square x negative. So omega is pi. So put omega as pi. Omega is nothing but pi. X is basically 3. So the answer to that is minus 3 pi square meters per second square. If only the magnitude is asked, then it will be 3 pi square meters per second square. That is the answer. It is lesser than the maximum value. What about the speed at 3 seconds? Use this formula. Omega root a square minus x square. Omega do I know? Yes, it is pi. A do I know? Yes, it is basically 5. X do I know? Yes, it is basically 3. So this will become pi into 5 square is 25 minus 9, which is 16. 16's root is 4. So it will become 4 pi meters per second. That's your speed at 3 meters, which is definitely less than 5 pi. So we found the speed, we found the acceleration at x equals to 3. Got it, my dear students, how to solve this question? Perfecto. Let's go to the next question coming up on your screen. Here it is. For a SHM, find where, for a SHM with amplitude A, find where is the kinetic energy equal to potential energy, number 1. Also find how many times this happens in one oscillation, in one complete oscillation. How many times do you think this occurs? That is the real question over here. Let's try to solve this. Come on. Ayo, votes are increasing, likes, come on guys. Smash the like button already. Yep. Come on. Think about this. Yeah, just 1 second, guys. And my AC also stopped working. Amazing. So let's do this question. Find where is kinetic energy equal to potential energy. So kinetic energy equals to the potential energy. I think we know the formulas for both kinetic and potential energy. Potential energy, the formula is half k a square. kinetic energy, the formula was half k a square minus x square, if you remember correctly. I had given you all these formulas right over here. Half k a square minus x square is kinetic, potential is half k x square. When you add them, you get half k a square. Okay, perfect. So let's see what do we get then. Now half k cancels, so a square minus x square, correct, is basically a square. Therefore, a square, yeah, ayo, what just happened? Did we, oh, sorry guys, I wrote a square over here, by bad. It was supposed to be half k x square. Potential energy was half k x square, not a square, my bad. Okay, now it will be fine. Half k cancels, so a square minus x square will be x square. Therefore, a square will be x square and x square will make it 2x square. Therefore, x square will be a square by 2. Therefore, x will be plus minus both a by root 2. So at both these locations, you will see potential energy will be equal to kinetic energy. If you remember the graph which was here like this, yep, it was like this. This was half k a square line. Then you had your kinetic energy graph like this, and the potential energy graph was basically like this. So one place is over here, which is minus a by root 2, and the other place is here, which is plus a by root 2. Both these places, kinetic and potential energies are equal. Now the next part of the question is, how many times does it happen? Many people, I have seen them answering this, sir, once here, once here. So 2 times. The answer is not 2. The number of times this happens, once while going like this, once while coming back, once while going here, and once while going here. So 1, 2, 3, 4. 4 number of times this will happen. Lot of people make this mistake and they say it is 2. It is not 2, it is 4. Because this point is going to be traced 2 times. Once while going like this, again while coming back. This point while going here, and again while coming back. So it crosses it 2 times each, 2 such points, so 4 times. Is this absolutely clear, my dear students? Okay, perfecto. Let's move to the next question coming up on your screen. Here it is. At t is equal to 0, x is equal to, let's say 10 by root 2 meters. Maximum speed is 20 pi meters per second. Spring constant is, let's say, pi square, or yeah, pi square Newton per meter. Mass is, let's say, 9 or let's say 16 kg. Question is, find number 1 time period, number 2 omega, number 3 phase constant, number 4 equation of SHM. All these things you need to figure out. Equation of SHM. Also, yes, amplitude also you will need. Very, very interesting question. I think easy parts we can do first. K and M is given. From K and M, the one thing that you will get easily is the time period. And time period is and time period is 2 pi under root mass by spring constant. So 2 pi, mass is 16, spring constant is pi square. So 2 pi, 16's root is 4, root of pi square is pi, pi cancels, 2 4s are 8 seconds. So the time period is 8 seconds, so we can easily get that part. So time is easily done. Omega also we can easily get it. Omega will be 2 pi divided by time period. So 2 pi divided by 8. So it will be basically pi by 4 radian per second. So omega also we have obtained it. Omega also we have obtained it. Is this clear till this point, everyone? Okay, just from the values of m and k, nothing else. Now the next part is find phi, also the equation of SHM. I think this data is given with a specific purpose, maximum speed and all of that. Because maximum speed is given, I think we can find the amplitude also. Observe how. Maximum speed is basically a omega and the maximum speed is 20 pi. So 20 pi is over here. Amplitude I don't know. Omega is basically pi by 4. Omega is basically pi by 4. Pi cancels. So what do I get the amplitude as? Check this out. 20 into 4, 80. So 80 meters is the amplitude. Okay. What next, sir? Once you get the amplitude, what do you do with it? Because amplitude is not even asked. Phi is asked, sir. Okay, no issues. Don't worry. Phi is asked, right? So use this piece of information when time is 0. Use this piece of information over here. X is a sine omega t plus phi. X is 10 by root 2. Amplitude, what is the amplitude? Amplitude is 80. Amplitude is 80. Actually, I had to give this as 80 by root 2, my bad. This was supposed to be 80 everywhere. This was 80 by root 2. Okay, 80 by root 2, amplitude is 80 and this is sine. Time is basically 0 plus phi. 80 cancels, so I will get sine of phi is 1 by root 2. Whose sine is 1 by root 2? Quickly think and tell me. Yes, Irfan, it will be enough. Whose sine is basically 1 by root 2? Correct. The answer is 45 degrees, which means that phi should be pi by 4 radian. So we have found the value of phi also. So equation of SHM, very easy now. Just substitute everything back over here. Therefore, it implies X will be amplitude was 80. We just got the amplitude from here, 80 karke. Okay. And then you have sine over here. What was omega? We got omega over here as pi by 4. So this will be pi t divided by 4 plus phi, which is basically pi by 4. So this is the correct equation of SHM, but the answer will be in meters. We found this also. So this is how you can solve problems on equations of SHM. Correct? Okay, perfect. Now let me also give you some more things over here. Obviously, sometimes for simple harmonic motion, right, for SHM, remember one of the thing is X is a sine omega t plus phi. This is given to you. Sometimes it will be given acceleration is directly proportional to x. That is, acceleration is directly proportional to the position. That will be given to you. Sometimes it will be given to you the force is proportional to x. The force is opposite and proportional to the displacement. It is opposite, that's why the minus sign. Sometimes the force might be some constant minus kx, that is also okay. That constant does not matter. Even if there is a constant, ignore it. As long as it is having minus kx in that equation, you are sorted. Another time you might also get that the potential energy is proportional to the square of the x term. That means the potential energy is a quadratic function of the position. position square. In any of these situations, either situation 1, 2, okay, or situation number 3 or situation number 4, all these are SHM's equation only, and every time you will see that the value of omega will be root of whatever k comes over here, or the time period is basically 2 pi under root of mass by k. Every single time for any kind of SHM. Every single time. Which means, just to give you an example of this, say I tell you, listen, the force acting on a particle is 10 minus 4x and the mass of the particle is basically 2 kg. You don't even have to think too much. It is definitely a SHM because it is of the form F is equal to constant minus constant. It is constant minus kx. Array. Constant minus kx. So comparing, you can easily get time period 2 pi under root m by k. So 2 pi under root mass is 2, k is nothing but 4. So this will be 2 pi 1 by root 2. Root 2 will cancel because 2 by 4 was 2. Root 2 will cancel. So it will become root 2 pi. So time is root 2 pi seconds. Easily you can solve these kind of questions. Sometimes again you might be given that, hey, listen, that the potential energy of the particle executing SHM is, let's say, 30x square. 30x square, and the mass of the particle is, let's say, I don't know, maybe 6 kg or something. It is definitely a SHM. It is definitely a SHM because you can see potential energy is of the form half k into x square. You can see x square over here. By the way, even if there is a constant, don't get scared over here. Just say, for example, even if half k x square plus some constant is there, don't worry about that constant as long as your potential energy is proportional to the square of the position. Don't worry about that constant. Forget it. Just forget that constant. So even if it was 30x square plus 45, don't worry about that 45. Just remember, it is just some constant. You don't have to worry about it. Just worry about this half kx square. Comparing, you will see 30 is equal to half k. Therefore, the spring constant is 60 newtons per meter. Therefore, the time period will be 2 pi under root. Mass is 6, k is basically 60. So it will be 2 pi by root 10. So that is basically the time period of SHM. So all these places, any of these forms, force is proportional to a negative kx, or potential energy is proportional to position square, or x is this. We have already seen these equations, that's why I'm not showing it to you again. All these places you can directly use the equations of SHM, which also means, imagine if by chance there was a spring mass system like this over here, then you might think, sir, it is vertical now, gravitational force will act. I know gravitational force will act. So because of that gravitational force, what will happen? The spring will get extended like this, all of that, correct? And it will have some extension x. It will have forces like this. mg will be there, and there will be kx over here. So the net force on that mass will be mg minus kx. mg minus kx. Can you see this is like a constant term which won't matter? This is what matters. Hence, the time period is still going to be 2 pi under root m by k. So constant force does not matter. Constant force does not matter for your SHM. Is this absolutely clear? Constant force does not matter for your SHM. Keep that in mind. All right. Similarly, if somebody just tells you, listen, the acceleration of the particle is given by minus 24x square, sorry, minus 24x, and the mass of the particle is 0.5 kg. Can you find the omega? Can you, sorry, not omega. Can you find the time period? Can you also find the spring constant? This kind of question can come. So what will you do? The moment you look at this, acceleration is minus 24x. We know acceleration proportional to position is again SHM only. You are just using this equation. Correct. So comparing this, acceleration is minus omega square x and acceleration is minus 24x. You can clearly see minus minus x cancels, so omega square is basically 24. So omega is root of 24. 24 is 4 into 6. So it is basically 2 root 6. Omega is basically 2 root 6 radian per second. Okay, so we got omega. From this we can definitely get the time period, which is 2 pi by omega. So it will be 2 pi by omega, which is 2 root 6. So hence answer will be pi by root 6 of a second. So that's your time period. We got this. I want to find out the value of k, which is the spring constant. How do I do that? We all know omega is the root of k by m. Omega, we just got it. How much was it? 2 root 6. K, I do not know. Mass 0.5. Square both sides. 2 root 6 was actually basically coming from here. So it will be 4 into 6. K by 0.5 square. 0.5 square. Therefore, K will be 4 multiplied by 6 multiplied by 0.5, which is half square. Half square is 4. 4, 4 cancels. Answer will be 6. So K will be 6 Newton per meter. K will be 6 Newton per meter. Done, dusted. Very simple and easy things. So all models of question I am trying to show you for SHM. Very few people will tell you that these are things which you can use. All the 4 different applications. Sometimes you might have a combination of springs. You might have a combo or combination of basically your springs. And when you get like that, don't get scared. First combination is when the springs are just connected in series, K1 and K2, basically series. The second combination is when the springs are connected in parallel. You might think I can do it like resistors in series and parallel. Yes, you can. But when you do that, keep one thing in mind. It is exactly opposite of resistors. It is like capacitors. So springs in series is like capacitor in series or resistors in parallel. So the equivalent spring constant is 1 by K1 plus 1 by K2. It's like resistors in parallel formula for series. For parallel, the equivalent spring constant is just like in series. So for resistors, so Kp is just K1 plus K2. Kp is just K1 plus K2. Very straightforward, guys. Is this absolutely clear, everyone? So just for the sake of example, imagine there were questions like this where you have to find the time period. There is one spring here, another spring here connected to a mass. This is K, this is 2K. Can you find the time period? Then another example like this where you have a big wall over here, another 1K over here, another 2K over here, and this is connected to a mass over here. Another example, one spring here, K, this is that mass, and another spring over here, 2K. How do you find the time period in every single case? So starting off with the first example, these two are basically going to be in series. So 1 by Ks, you have to use parallel formula for resistors, is 1 by K plus 1 by 2K. So LCM is 2K, so it will be 2 plus 1, which is basically 3 by 2K, or Ks is basically 2K by 3. Therefore, time period will be 2 pi under root mass by K. K is 2K by 3. That is the answer. That is the answer. Is this clear, my dear students, how we did this? So when springs are in series, use parallel resistors formula, 1 by K plus 1 by K, that one. And then do not forget to take the reciprocal in the end. A lot of people forget to reverse this. You have to take 2K on the top, 3 below. 2 pi under root 3m by 2K. Cool? These two springs are definitely in parallel, sideways arrangement. So they are definitely in parallel combination. In parallel combination, you just have to add them. So K plus 2K will give me just 3K. So time period will be 2 pi under root m by effective constant, which is 3K. Effective constant, which is basically 3K. Now, carefully analyze this. These two springs actually are not in series, they are in parallel. Let me tell you why. Because imagine a lot of people think they are in series, so a lot of people will use this method. No, imagine somebody extends this mass goes over here, and then this guy gets compressed. See how the forces on this mass will be. This mass, due to this spring, will experience a force this way. This spring will get compressed, so it will push it this way. Don't you see the forces are in this direction? Don't you see the forces are towards the left side? When I have moved the mass towards the right side. When I have moved the mass towards the right side. Both the force due to spring 1 and spring 2 are towards the left side. Now imagine doing the same thing for this. If you move this towards the right side, both the springs will get elongated. It will apply a force here and here, F1 and F2. The forces look exactly similar towards the left side for a disturbance towards the right side. So force wise, equation wise, there is nothing different in this and this. So this is also actually in parallel. They are also in parallel, so you have to use this. Alright, guys, there is again no electricity, so I might have to go a little bit dark. Don't know whether I'm seeing. Okay. Luckily, electricity came now again. Thank God. Okay, perfect. Then you can have some more weird combinations like this also. Say for example, you are given one spring is here, another spring is here, another spring is here. This is connected to a wall. This is 2K, this is 2K, this is K, and this is a mass. How will you solve this kind of a question? Okay, how will you solve this kind of a question? So first of all, you will realize one thing, that these two springs are in parallel, so you can convert it into one single spring, right? One single spring. So it will be just 2K plus 2K. It will be just 2K plus 2K, which is going to make it 4K, correct? They are basically in parallel. In parallel, you will treat them like series resistors. And now it is connected to this spring, this mass as it is. Now they both are definitely in series, and when they are in series, you have to use parallel formula. You have to use basically parallel formula. So 1 by Kp is 1 by K plus 1 by 4K. LCM is 4K. So 4 plus 1, which is 5 by 4K. So Kp will be 4K divided by 5. 4K divided by 5. Hence, the time period will be 2 pi under root mass by spring constant, which is 4K by 5. Root of 4 root of 4 is basically 2. So 2 cancels. So pi root 5m by k. That is the time period. That is the time period. Correct. Very good, Madhumati. Excellent. Then sometimes, they might also give you a question like this. They might ask that you have a spring of constant k and you divide it into n parts. You divide it into n number of parts. So what is the spring constant of any one such part? What is the spring constant of any one such part? How do you solve such a question? First of all these springs, if you join it back together, okay, imagine if you join all these small teeny springs, n number of them together, you should get back the original spring. They are just n springs in series, n number of springs in series. And in series, if each one of them is k1, 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 etc. So 1 by k1 plus 1 by k1, like that, n number of times if you do it, you should get back the original spring of constant k. So this will be n by k1 is 1 by k. Therefore, k1 will become k divided by n. So very interesting thing, sorry, not k divided by n times of k. Very interesting thing, when you break a spring into n parts, when a spring is broken into n number of parts, the constant becomes n number of times. Very, very important. The constant will become n number of times. It will multiply n number of times. The reverse also will hold true. The reverse also will hold true if you take n identical springs, each of constant k, and join them together to get one single spring. Lot of you will think that I will get the spring constant of nk. Wrong. When you add these springs, this constant 1 by, let's say, k1 will be 1 by k plus 1 by k, like that, n number of times, which will be n by k, which will be n by k. So therefore k1 will be k by n. So when n number of identical springs are joined, the spring constant gets divided by n. The spring constant gets divided by n. Yes, correct. These are some questions which you might get on the combination of springs concept. There is one problem which you might get very rarely, but I will just give it to you. This kind of problem is called as a reduced mass system. Reduced mass system. Reduced mass system, where you might be given, listen, there is one mass m1 over here, one spring over here, and another mass m2 over here. This mass will go back and forth, this mass will go back and forth, it will oscillate. You can convert it into that same spring constant k, but one single mass, which is called as the reduced mass. This m over here is called as the reduced mass, meaning instead of 2 you are getting one mass which behaves exactly the same way with the same time period. So that reduced mass is m1 m2 divided by m1 plus m2. Therefore the time period will be 2 pi under root m by k, but that m will be this m reduced, whatever you got over here. So you can replace those two masses with one single mass. Sometimes, very rarely, you might get a question. All right. So having said this, probably it's good time that we take a break before we go ahead. Okay. So let's take a break, guys. Which slide should I leave? This slide looks good only. Hello. Yo, welcome everyone. I hope you had your teeny mini break and maybe your lunch too. All right, let's go ahead. So we started off with this chapter of SHM, guys. We have seen all the equations, time period, frequency, angular frequency. Then we also saw how velocity is related. We also saw equation for accelerations and obviously the graphs, which were interesting. And then we also went for energy equations. Yep. And we have also seen different kinds of problems, even the combination of spring kind of questions. Yes, series behaves like parallel, parallel behaves like series. That is what we have seen. All right, so let's proceed ahead now to some more questions coming up on your screen. All right. Welcome back, Krishna, Madhumati. Hi, Sneha, Disha. Welcome back. Yes, I think maybe 1 hour or so I'll be conducting a separate class for phasors and combination of SHMs, because that will be common for even the waves part. So I was thinking, why not have a separate dedicated session for it. Today in the second part we'll be just doing angular or rotational or torsional SHM. That's what we'll be doing. All right, so see this. You take a spring like this and connect a mass, or let's say you have some elastic rubber band and you have attached some mass to it. You stretch it and leave it, it will go back and forth. It will go back and forth like this. You pull it and leave it, it will go back and forth like this. These are examples of linear simple harmonic motion. Linear means they are going along a line. Translation. There are examples where it is rotating. So things like, you take a mass, attach it to a thread and leave it. Or you have supported some rod and connected it to some mass over here, and then you twist it and release it, or you release it from this side, it will go back and forth like this. It will go back and forth like this. All these are cases of angular simple harmonic motion. They are not along a line, they are along an arc, they cover an angle. So that is angular SHM. This is where you twist something, release it, it goes like this. It goes oscillating like this to and fro. So imagine you are sitting in a swing. Everybody would have sat in a swing, right? You go behind and leave yourself. You will go like this, like in a Columbus joyride, and then you will come back. Again, you will go like this and you will come back. That is your pendulum, simple pendulum kind of motion, pendulum motion, back and forth. Okay. But imagine you are in a swing and you turn that swing like this and leave it. Then you will go like this, stop. Again go like this and stop. Again go like this and stop. So this is your, again angular harmonic, simple harmonic motion, but you are twisting that object back and forth. So that is why this is usually called as torsional pendulum. This is usually called as your torsional pendulum. Torsional pendulum. This is just your simple pendulum. This is just your simple pendulum. There is also another situation where you can just take some object and just hinge it over here, support it over here, okay, and it will go back and forth like this. Say for example, I take my phone and I hold one of the cameras maybe over here and just leave it. It is going back and forth. It's not a point mass which is attached to a thread like a simple pendulum. Rather, it's a big mass with some dimensions and it is attached somewhere and it is going back and forth. Yes, this is also a pendulum, but then this is called as a physical pendulum. This is called as a physical, and since this was simple, sometimes this is also called as compound pendulum. Compound pendulum. So before the break, we have seen linear SHMs where objects are going back and forth along a straight line, they are translating. After the break, we are going to see these three things: simple, physical and torsional pendulum, which are a part of angular SHM, meaning they will displace the arc of a circle, thereby displacing an angle towards the center. So that is what we are going to do. Okay, so is this three distinctions clear? Simple pendulum, torsional pendulum. Okay, simple was like this, back and forth, and this was compound, basically a big body attached at a point, not a point mass. These are the three things. So what will be different for an angular SHM, you might ask? Say for example, say this is a circle which we consider. So now you always have a reference line. So let's say this is our reference. In this case, the reference also happens to be our mean position, and this over here is extreme left and this over here is your extreme right position. The terminologies over here which we use, this complete angle, this complete angle from the mean to the extreme or mean to the extreme on this side, that I will call it as theta m. This theta m is called as the angular amplitude. Angular amplitude. As you can see, it is nothing but the max angular displacement with respect to the mean position. From the mean, maximum here, that's the amplitude, but angular wise. Usually it is expressed in radians. So the particle will go back and forth like this along this particular path. It will once go here, then come back here, then go here, and again come back here. So it is keeping on going back and forth. So this is basically nothing but your angular SHM. This is your angular simple harmonic motion. Angular simple harmonic motion, which we just discussed. Is this point clear? Other things are still the same, like the time period and frequency and all of that. F is still 1 by t. Omega is 2 pi by time period. 2 pi by time period, which is also 2 pi f. So this is your angular frequency, not speed. This is angular frequency, and this is just your frequency. These formulas are still the same, t still being the time taken to complete one oscillation. This is still the same formula. Now additional formulas which look very, very similar as you saw in linear SHM. Very, very similar looking formulas. Observe this. If you are here at some random instant of time, if you are here, and this is the angle which you have displaced. Remember, the total angle displaced maximum will be theta m. Theta is at that instant angular position. So theta is not maximum. This is just angular displacement with respect to the mean position. Instead of x you have theta, instead of amplitude you have theta m. So equations are very similar. Instead of x is a sine omega t plus phi, you will have theta is equal to theta m sine omega t plus phi. Exactly similar looking equation. No difference at all. Instead of x, you have theta. Instead of amplitude, you have theta m. And this is anyways the same thing. So theta will keep on fluctuating. It will keep on going back and forth between these two extremities. Then what about the velocity? But now we are not going to talk about any random velocity. It is angular velocity. So you will have angular velocity, and not just that, you will also have angular acceleration. The symbol for angular acceleration is alpha. Remember, circular motion. The symbol for angular velocity is omega. But there is a problem. A lot of students get confused between this omega here and this omega here. Remember, this omega is a constant. It is angular frequency. 2 pi by t, t is a constant, 2 pi is a constant, this is a constant. Please mind that. But this omega over here is angular speed. It will keep increasing, decreasing, changing direction, angular velocity, angular frequency. So I cannot use same symbols. So hence it is usually written down as theta dot. Theta dot. What is the dot representing? The dot represents derivative. So when I say x, x dot means dx by dt. When I say x double dot, it means d square x by dt square, second derivative of x. So a dot represents derivative. So rate of change of position is velocity, rate of change of angular position, displacement, is nothing but angular velocity. So hence I will say angular velocity, which is nothing but rate of change of angular displacement. Okay, so that omega I can't use, so instead I will use theta dot. That theta dot will be just like velocity formula. Instead of amplitude you will have theta m, omega will be omega only. This you will have sine omega t plus phi. Please note, this is angular frequency, which is a constant, not to be confused with angular velocity. It is not angular velocity. Please mind that. I am repeating that over here again. Similarly, you have angular acceleration, and that angular acceleration alpha, which is also theta second dot, meaning second derivative of position. Dx by dt, dx by dt is dx by dt. So second derivative. So this will be minus a, instead of amplitude you have theta m, omega square sine, you have this omega, you have sine omega t plus phi. So that is the answer. Just like a is minus a omega square sine ax plus t, same thing over here also. So 1 second. Sine omega t plus phi. You can also write acceleration as minus omega square x. So instead of x, you can also write theta. That is also permissible. There is nothing wrong in it. Even over here, instead of finding velocity like this, you can also write velocity as omega root a square. A square means theta m square minus x square. X over here is theta, so minus theta square. That was the same kind of equation which we wrote in linear SHM. So this is also valid. Either you can use this or this, both are okay. So I'll put or over here. You can also use this or this, or. Okay, all the equations are very, very similar. All right. So are there equations for forces and torques and energy also? The answer is yes. So let's have a look. So again, you move this over here by some angle theta, and there is now not a force but a torque. There is a torque acting on it. Let's say that torque is this. So that torque will be moment of inertia into alpha. Moment of inertia into alpha. Not just that, that torque is restoring in nature. Actually speaking, this torque is restoring in nature. That means it will try to bring it back. It will try to pull it back. That's why restoring. So that torque is actually minus k times of theta. Minus k times of theta. Like you have force is minus kx, this torque will be minus k times of theta. If you rotate it like that, the torque will try to bring it back. Minus sign is because I have assumed the wrong direction of torque. Actually the torque will be opposite. So deliberately I have written it like that, because one side we always take positive, other side will be negative. So the moment I show torque this way in the same direction of theta, this minus indicates torque and theta can't be of the same sign. If theta is positive, torque will be negative. If theta is negative, torque will be positive. That means they are always opposite to each other. So that is why that negative sign. This negative sign indicates that the torque is opposite to the displacement. That's what it signifies. So what is this K then? What is this K? It is not spring constant over here. Usually it is called as the torsional constant. Usually it is called as the torsional constant, and mind it, the unit is not Newton per meter. It is Newton meter per radian. Newton meter per radian. Newton meter, bring theta below, per radian. So the time period of oscillation will be 2 pi under root. Instead of mass, you will have this guy over here, which is moment of inertia. Instead of spring constant, you have torsional constant. Same thing even for angular frequency. This is your angular frequency, not speed. This omega will be root of spring constant replaced by torsional constant, mass replaced by moment of inertia. So all the formulas are still applicable. It's just that mass is converted into inertia, moment of inertia, spring constant into torsional constant, force into torque, displacement into theta, velocity into angular velocity, acceleration into angular acceleration. So if you know linear SHM, angular SHM is a very easy laddu thing. Yes. Is this clear? Everybody till this point? Okay. Let's have a look at this. It's a disc of mass 2 kg and let's say 3 meters. This particular rod, nothing has been mentioned as of now, but it is told that for every 30 degrees, the restoring torque is 50 5 by 3 Newton meter. Is basically 5 by 3 Newton meter. The question is, if somebody now disturbs the disc, if you rotate it like this, it will definitely oscillate. It will definitely oscillate back and forth. The question is, can you find the time period of this torsional pendulum? This is a basically torsional pendulum because you are giving a torsion, meaning you are twisting it. You are twisting this rod plus the disc. So that is why I can call it as torsional pendulum. Torsional pendulum. Can you find the time period of this particular torsional pendulum? All right, let's do this. There are a couple of things which we need to find. What is the torsional constant? What is the moment of inertia? Only then we can find the time period using this. Okay, so let's do one thing. Let's try to find everything about it. Starting off with moment of inertia. Starting off with what is the moment of inertia? Well, the moment of inertia of a disc, we all know, is mass radius square divided by 2. Mass is 2 kg, radius is 3 divided by 2. Hence, it is 9 kg meter square. That's moment of inertia. Spring constant replaced by torsional constant, that is not given, but this is given. So, using the concept, torque is torsional constant into theta magnitude wise. The torque is 5 by 3 Newton meter per radian actually. That's okay. That's can be converted into radian later on. So, torsional constant, don't know, theta is 30 degree. 30 means pi by 6 radian. So, see what happens. 3 cancels with 6 2 times. So, K will become 2 5s are 10 divided by pi Newton meter per radian. Newton meter per radian. So, K also we got. So, last step is finding the time period, which is 2 pi under root instead of mass inertia, spring constant replaced by torsional constant. Moment of inertia 9. So, put it over here. Spring constant, which is torsional constant, 10 by pi. Okay. Root of 9 is basically 3. Pi's root as it is, 10's root, I can keep it as it is. So basically this will become 6 pi root pi by 10 seconds. That is the answer. 6 pi root pi by 10 seconds, that's the time period. Got it? How to solve a question on torsional pendulum? You can find K if this kind of information is given. You can also find moment of inertia if you know whether it's a disc, sphere, whatever it is. And time period is 2 pi root instead of mass, inertia, spring constant, torsional constant. Exact ditto method, no difference at all. Correct. Very good, Madhuvati Krishna. Tomboy understood. Very good. Sneha. All right. Moving on. Next, let's discuss simple pendulum. And then we'll also go to compound pendulum also. Actually, we can do compound first. Okay. So, let's do physical or compound pendulum. Physical pendulum. In case of a physical pendulum, you might have a body like this, and it is hinged maybe over here. This is the hinge point. The center of mass of the entire body might be here. This is where the center of mass is, and exactly from the center of mass we know the weight will act. So mg will be here. Usually the center of mass should be vertically below the hinge point, then it will be stable. But as you can see very well over here, the center of mass has been pushed away from the equilibrium position by some angle, like you can see over here. Okay, clearly I can join this line, and you can see that definitely there is some angular displacement, theta. You have displaced it. Ideally, center of mass should lie here, then it would be in equilibrium. Think about it. If that same mass was like this over here. The center of mass was here. Then this would be stable equilibrium. From its stable equilibrium, you have moved it. So definitely, it's going to try and come back. mg's component will be there over here. One of the component will be like this, and the other component will be like this. It's obvious that since this is theta, even this is theta. So mg cos theta will not create any kind of torque, but it is mg's sin theta which creates torque. So this is going to create a torque, and let's say this distance is also known to me. How far is center of mass from the hinge? Let's say I call it as d. So the restoring torque magnitude, the magnitude of restoring torque is going to be, observe this carefully, r cross f, right? R f sin theta. What is r? R is over here d. What is the force? The force is sin theta. Already it is mg sin theta. Mg sin theta. I have already taken the component. Mg was the force. Angle between them was theta. So mg sin theta. Already done. Yes. So dmg sin theta is the magnitude of the torque. But for small angles, very, very important, for small angle, what will happen? Sin theta approximately equals theta. So therefore, that torque which we are talking about approximately is dmg multiplied by theta. dmg multiplied by theta. Torque is something into theta. This something naturally should be your torsional kind of constant. This is your torque constant. Yes, this is your constant. Obviously, then I will get the value of the time period. So the time period will be 2 pi under root. Whatever that constant comes will come below, and here you will have moment of inertia on the top. So therefore, the time period of this physical or compound pendulum will be 2 pi under root moment of inertia divided by constant, which is mgd. This is the answer. Again, this is something which you have to remember. 2 pi under root I by mgd. Cool. So this is how you find the time period. All these other formulas were also very important. What I've blocked over here. Torque is minus k theta. This you know from Newton's law in rotation. All these are standard formulas again. Let's do a question on this so that you get an idea. Imagine somebody just takes this rod like this. This is a rod of mass m and length L, and somebody disturbs it like this. So if you disturb this particular rod and release it, question is find the time period of this particular oscillation. Find the time period of this particular oscillation. It will keep going back and forth. That is the question. All right. First of all, you should realize that this is actually a physical pendulum, not a simple pendulum. Why is it a physical pendulum? It's not a point mass, it's a distributed mass, it's a big body. So for physical pendulums, what you need to do, locate the center of mass, see how far that distance is, mg, and moment of inertia. I need all of these things. So let's start one by one. Where is the center of mass? The center of mass is obviously going to be here, and the center of mass is at a distance of this d will be the length of the rod divided by 2. That's the first thing. Next thing, what's the moment of inertia of the rod about that particular hinge? This is the moment of inertia of the rod at the end. At the center it is ml square by 12. At the end it is ml square by 3. Lot of people forget this formula. I am reminding you, it is ml square by 3 using parallel axis theorem. Okay, sir, then what is the time period? The time period is 2 pi under root I divided by mgd. Okay, 2 pi is there, moment of inertia ml square divided by 3. M is m, g is g, d is l by 2. So what will the time period come out to be? It will be 2 pi under root, gone, ll gone, so l 2 3 g. That is the answer. 2 pi root 2l by 3g. Yes, that's the answer. Jayantika, maybe more, 15 minutes, 20 minutes. That's how the session will be. Alright, that's how you solve this question on physical pendulum. Let's take up one more example of physical pendulum. Let's see if you guys can solve this. You take a ring of mass m and radius r, and it is hinged over here. And it is released after disturbing so that it oscillates back and forth like this. Question is again, find the time period of oscillation. Again, start by seeing where the center of mass is. Center of mass of the ring is over here. So this distance which we should calculate is the radius of the ring. Okay. What is the moment of inertia of that particular ring about the hinge point? Use parallel axis theorem. It's moment of inertia about center of mass plus md square. Moment of inertia about center of mass is mr square. The distance by which the axis has been shifted is d, which is also the radius. So it is basically 2mr square. Now we can find the time period. 2 pi under root I divided by mgd. So 2 pi under root, what is the moment of inertia? 2mr square. What is mass m? G, dr. So what will I get? 2 pi root, cancelled, rr cancelled. So 2r by g. That is it. So 2 pi root 2r by g is the final answer. Is this absolutely clear, my dear students? How do you solve the questions on physical pendulum now? Okay, all these are examples of physical pendulum. I've already shown you how to solve torsional pendulum using these formulas to find the time period. Now, you might also get a question like this. Observe this, where it is on simple pendulum. Okay, so a simple pendulum is where you have a point mass attached by a massless rod or a massless thread. Unlike in physical pendulum where it's a distributed mass, it's not a point object. The disc, the ring, the rod, all these are distributed objects. It's not like a point. So when you have a point mass when you have a when you have a point mass connected to a hinge point with a massless rod or a thread, that's a simple pendulum. Obviously, again, the same things will happen, like the weight will be there and there will be two components. There will be two components of the weight, and one of the component will be mg sine theta, which is responsible for the torque. Mg cos theta won't create any torque. And by the same analysis, if you try to find the time period, which is given by 2 pi under root moment of inertia by mgd, observe now what will happen. It's a point mass. For a point mass, the moment of inertia about this hinge point is mr square. R here is L, so L square. Then the mass m is m only, g is g only, d. Center of mass of this is at a distance of L. Center of mass is at a distance of L only. Yes, center of mass is here, hinge is here, the distance is L. So what will happen? MM cancels, LL cancels. So what will you be left with? You will be left with 2 pi root of L by G. So that is the time period. Very important formula again. Time period of a simple pendulum is 2 pi root L by G. 2 pi root L by G. Perfect. Very important formula. Now there are some special variations in this which you should again know. I will tell you about that as well. Special variations is, see, number one, this is the time period if on Earth, if it is on Earth. But let's say our whole system of that particular pendulum is inside some lift, or other planet. Then what will happen? Inside the lift, the gravity perceived will be very different. Maybe the lift is accelerating up, maybe it is accelerating down, or maybe it is accelerating somewhere else. G is different. So then in such cases, when you have to find the time period of the pendulum, you will use 2 pi root L by G effective. G effective, very, very important. This G effective will be G plus A and G minus A depending on whether the lift is going up or down. So if the lift is accelerating up, then G plus A. If it is accelerating down, then G minus A. And if the lift is accelerating sideways, then the G effective will be root G square plus A square. G square plus A square, you have to use Pythagoras. Yes, if it is going sideways, then the gravity due to the lift's motion will be this way. Actual gravity will be like this. G effective will be in this direction. So because of that, you have to take square of A and square of G and put it under the root to get the resultant value. That is what will be different depending on whether the lift is going up, down, or on some other planet. Another important thing is about the seconds pendulum. So a lot of people forget about what this seconds pendulum is. A seconds pendulum is a pendulum. A seconds pendulum is a pendulum whose time period is 2 seconds. It's basically tick, tock. Tick is 1 second, tock is basically again 1 second. Tick, tock, 1, 1, total 2 seconds. That is a seconds pendulum. So if you put the time period as 2, you will get 2 pi root L by G, 2 cancels. So therefore, you will get 1 is equal to pi by root G into L. But pi and root G are roughly same. So therefore, you will get length is approximately 1 meter for a seconds pendulum. Very, very important thing. Please remember pi is root G. Yes, pi is approximately root of G. Pi value, remember, is 3.14 and G value is 9.8. Root of 9.8 is roughly 3.14. So hence pi is root g. So they cancel out and length is 1 meter. This is another thing which you must know. Let's do some questions on this. A pendulum of length 40 meters has a dash time period, question mark, if it's taken in a cabin which moves horizontally, at 20 meters per second square, find the new time period. Find the new time period. That is the question. Let's try and solve this. First thing, a normal pendulum 40 meters length, what is the time period? So direct application of formula, time period will be 2 pi root of L by G. So 2 pi is as it is, length is 40, G is 10. So that will be 2 pi root of 4, which is nothing but 2. 2 2s are 4. So 4 pi seconds is the first answer. So this answer is done. So this is 4 pi seconds. This is 4 pi seconds of time period. First answer is very straightforward. Yes or no? Correct. All right. Very good. Thank you for making the likes cross 100. Yep. What about the second part? The moment you put it inside a cabin, this particular pendulum, and make it accelerate at 20 meters per second square, the effective gravity G effective will become root of, I just told you, G square plus A square. I just gave it to you over here. If you have a cabin which goes horizontally, root G square plus A square is G effective. So hence over here also G is basically 10, A is basically 20. So 10 will come outside, 1 plus 2 square is 4. So it will become 10 root 5 meters per second square. So coming back to the new time period, it will be nothing but 2 pi root length, which is 40, G effective is 10 root 5. So it will become 2 pi root of 0 0 cancels, so root of 4 will be 2, and I will have root of 5. So it will become 4 pi by the fourth root of 5. So that is the new time period. That is the new time period. As simple as that. Is that okay, everyone? Very good. Awesomeness. Awesomeness. Moving on to another question. Root of root is fourth root, 1/4. So it is called fourth root, cube root, fourth root, fifth root, sixth root, like that. Normal square root means raised to the power half, right? So that is root of a root. So 1/2 into 1/2 is 1/4. So it is called fourth root of that number. Yep. All right. So coming up to the next question, a pendulum in a lift which can accelerate up or down has the ratio of time periods dash is to dash. That's the question. What's the ratio of the time periods of oscillation when the pendulum is inside a lift which can either go up or down? Okay, so let's try to solve this question. First of all, When you are going up, I told you the effective gravity will be G plus, going up is plus. So the time period will be 2 pi under root, I forgot to mention up and down acceleration, up and down of 5 meters per second square. I forgot to mention some value. Acceleration of 5 meters per second square. Okay, now it's fine. So 2 pi root L by, instead of G, you will put G plus A. That's all. So this will be 2 pi under root L by 10 plus 5, which is 2 pi under root L by 15. Similarly, when it is going down, the effective gravity will be G minus A. So time period will be 2 pi under root L by G minus A. So it is 2 pi under root L by 10 minus 5. So it will be 2 pi under root L by 5. This is while going down. So the time while going up upon the time while coming down. If you take the ratio of this, what will happen? Observe carefully. 2 pi, root L is the same. So while going up, root 15 is below. So while going up, root 15 is below. Again, while going down, root 5 is below. So if it is below, it will go on the top over here while going down. So that's it. Hence the ratio will be 5 and 15 goes 1 by 3 times. So 1 is to root 3. The answer is 1 is to root 3. Correct. That is the correct answer. So this is how you solve these simple pendulum related questions. It's not that difficult, like you can see. Okay. It's very, very straightforward. Correct. Very nice. Awesome. So fine, this is simple pendulum. Physical pendulum is also done. We do not have damped oscillations, forced oscillations in the syllabus anymore. It was there long time back, so don't have to study that, number 1. Number 2, we will do combination of SHMs and superpositioning as a separate class, because that will be required for waves also. So I'll take a separate class for that. Okay, I cannot confuse you with this. I mean, I can do it, but I don't want you to be confused in a single class. Cool. So any doubts still here, please let me know. Anything that you want to ask me, please let me know in the comments also. That's also perfectly fine. Hopefully you are able to understand all these things, all these concepts. All handwritten notes will be given to you as PDF in the Telegram, as well as the treasure box, the entire sheet which is maintained for all of you. So use that for your benefit. And yes, share this lecture, like this lecture, comment below this lecture. Yes sir, oscillated. So I want everybody to type the word oscillated, in the comments. So I want everybody to put this up in the comment section so that I know you have watched it till the end. Cool. All right. Take care, guys. Have a great time. Lovely day. And nice to see you all back after Diwali. And now is the second phase of our preparation. We are about to complete everything. So make sure you are on time. So make sure you are subscribing and liking. Okay. Bye-bye. Take care.